This is the last lesson in chapter 20, and it's very similar to a lesson in chapter 18 about capacitors in a circuit with a resistor. In your student folder, I put a PDF of a comparison of all the graphs and the equations involving capacitors in a circuit compared to inductors in a circuit. Now, what do I mean by an inductor? Again, an inductor is nothing more than a tightly wound coil of wire. It can be as small as your fingertip. It could technically be as big as your fist. I don't recall seeing any of them too much bigger than that. But if you put it into a circuit, we call it not an electromagnet, but an inductor. And the goal is not to pick up objects that are made out of iron and steel, but it's to regulate, to moderate, to choke the current so the current cannot change too much. The symbol for an inductor is that red curlicue that you see right there. And we can enhance the effect of the inductor if we were to put an iron core through the center of the loops. That would concentrate the magnetic flux lines that would be experienced when current goes through the wire. So the rest of this discussion requires you to remember what we meant when we talked about the back EMF, the pushback that happens when current goes through a wire, because as soon as current goes through a wire, it induces a magnetic field about that wire, which is usually nominal or can be ignored unless the wire is in a coil. If the wire is in a coil or a solenoid or a bunch of loops, each loop is in such close proximity to an adjacent loop that as the magnetic flux lines expand or collapse around one loop, it affects the current in the other loops. Now, equation 20.12 is Ohm's law, and the way we're going to look at resistance in this case is not so much as an object that work is going to be done on, where voltage is going to be used up as a current goes through a circuit from a power supply, from a battery. Instead, we're going to look at it a little bit differently. We're going to interpret resistance as a measure of the opposition to current. In other words, our goal here is for the inductor to minimize sudden changes or fluctuations in the current in a circuit. Now, the picture A at the top of the page shows a diagram of a very simple circuit with a single resistor in it. If there weren't any resistor, you'd have a short circuit, meaning the current would leave the battery out the positive end with all of its energy, all of its voltage per charge, energy per charge, all of its voltage, and there would be nothing for it to do other than heat up the wire and heat up the battery. That's what a short circuit would do. In picture B, instead of a resistor, we put an inductor. And then in the picture at 20.27, we will add both a resistor and an inductor. In chapter 21, we talk about circuits that have a resistor and a capacitor and an inductor. And then when you go into alternating current, you look at the effect of alternating current going back and forth, causing the flux lines to oscillate 60 times a second. And if those of you going into electrical engineering will spend a lot of time on that subject. Now, remember what inductance is. Inductance is a measure of the opposition to the rate of change of current. It chokes the current. It keeps the current from getting too big or too small too fast. And it's all because of the back EMF. And back EMF is that pushback you get as explained with Lenz's law. That's the reason for that negative sign in equation 20.13. And the letter L representing the inductance also is a function of just what is the inductor made out of? What are the mechanical properties of that inductor? And of course, it depends upon how rapidly that current is changing. That's your delta I divided by your delta T. And you can see that it is your proportionality constant. Now, look at figure 20.27. When we close the circuit, completing this circuit, the battery pushes the charge out the positive. It begins to travel clockwise. And of course, it's going to do so instantaneously. And as soon as it gets to the inductor, it's going to cause magnetic flux lines to grow, to expand into space around each loop, which of course is going to affect all the other loops that are nearby. And Lenz's law says that's going to establish a potential difference opposite. So you'll notice that the positive sign comes first and then the negative sign by the inductor. It's going to push back, keeping the current from reaching its maximum value. So the current has to back off a little bit. And when the current backs off a little bit, isn't quite as much, you don't get quite the change in the flux lines. And as a result, eventually, as you get this back and forth between the current trying to get to its maximum and the inductor trying to push back, eventually your current is going to reach its steady state value. And when the current reaches its steady state value, the rate of change is zero because the current is no longer changing. So you no longer have changes in your magnetic flux, especially around the loops of wire. And so that means that your back EMF goes to zero. And for all intents and purposes, now the inductor is not doing anything. Now, we'd like to know how long does it take to reach this steady state current? And for that, we have this idea of a time constant. Very similar, if not exact in meaning, to what we had with the capacitor. It takes time to reach the maximum current in both the capacitor and in the inductor. In the capacitor, the pushback occurred because of the fact that as charge accumulated on the capacitor, it made it harder for the next batch of charge to get to the capacitor. In the inductor's case, you've got the pushback from the magnetic flux lines that are expanding or contracting around each loop in the solenoid. Now, the time constant is going to be defined by equation 20.14, very similar to the way that we define the time constant for a capacitor. And a graph of this circuit would look something like this. And this looks, again, very much like the graph of charging up a capacitor. It takes a little bit of time before you approach your maximum value, represented by the horizontal dotted line E over R. You might remember that script E over R is Ohm's law. E over R equals I, the maximum current. And you asymptotically approach that horizontal line. Now, since you never actually reached that dotted line, we talk about the time constant. And you might say, well, where did this number 0.632 come from? Well, let's go to the next page and look at the equation that comes from calculus. A similar equation in calculus yields a function that's got the letter E in it, from which we develop the formula for half-life and the decay constant. Now here, you recognize that if I did not have the part of the equation in parentheses, 1 minus e to the negative t divided by tau. Tau is the Greek letter T for time constant here. If we didn't have what's in parentheses, you'd have I equals script E over R, which is nothing more than Ohm's law. Your maximum current would be script E over R, your electromagnetic force. But you're not going to quite get there, and that's because of what's in the parentheses. Now, if tau equals t, if tau, your time constant, has the same value as t, t divided by tau equals 1. You've got a negative sign there, so you have e to the negative 1. And e to the negative 1, if you were to look that up, equals 0.3679. And if you subtract it from 1, like you see in the parentheses, then you get that 63.2%, or that 0.632. So tau, the time constant, is how long it takes to reach 63.2% of your steady state current. Remember, capacitors, we talk about voltages because it takes more and more oomph or push from the power supply, from the battery, to push the charge onto a metal plate that already has some charge on it. In inductors, we talk about current because it's the fluctuating current that causes the pushback from the inductor as the magnetic flux lines expand and contract. Now, if we look at this math problem here, we've got a 12.6 battery. It's in a circuit with a 30 millihenry. See the mH, M is milli, millihenry inductor. We have a rather small resistor, 0.10 ohms. And again, you want to have your resistor in these circuits so you can avoid having a short circuit. The question says, what's the time constant? So your time constant, tau, is your inductance divided by R. And you can see that that equals 0.200 seconds. 0.2 of a second is how long it'll take for this inductor to affect the turning on of the current when you throw the switch, and how long it'll take to reach 63.2% of its steady state current. In letter B, find the current after one time constant. Here's where you take your voltage divided by the resistance to get your maximum theoretical possible current of 84 amps, and you multiply it by your 63.2% to get your actual current after one time constant, 1 tau. And then finally, find the voltage dropped across the resistance when t equals 0 and t equals 1 time constant. And again, we're using Ohm's law. And we're going to get 7.97 volts here. You can see there's quite a rapid rate of change in current, 150 amps per second. And remember that the current in a typical wall outlet is 15 amps. Of course, that's alternating current. Look at example 20.9, the formation of a magnetic field. It says, find the time required to reach 99.9% of its maximum value. So here your goal is to get to almost the total possible or theoretical amount of current that you could have in the circuit. And this requires a little bit of algebra 2 juxtapositioning of your terms and also remembering how to do natural logarithms. The last thing we want to look at is the fact that just like in a capacitor, we can store energy by charging up a capacitor and having one metal plate with an accumulation of charge on it, poised and ready to jump across to the other metal plate if we're not careful, but to surge back through the circuit when we open the circuit. It can do work for us. In an inductor, we are storing energy in the magnetic field of the electromagnet that is in the circuit. That's the inductor that's in the circuit. When those magnetic flux lines are created, they can do work when they collapse back to zero. And the amount of energy stored in an inductor is very similar in terms of how it looks to the amount of energy that is stored in a capacitor. You can see that both of them have to do with 1/2, and they kind of remind you of the equation of kinetic energy. 1/2 mass times velocity squared. Well, each of these equations are 1/2 either inductance current squared, or in the capacitor, 1/2 the capacitance voltage squared. Because inductors are all about current, the changes in current, and capacitors are all about changes in the voltage.